Kubernetes and AKS orchestrating. Number sign Kubernetes and AKS orchestrating containerized applications. Introduction. Kubernetes has become the de facto standard for container orchestration, and for good reason. It solves a fundamental problem. How do you run containerized applications at scale, keep them healthy, and make them accessible to users, all while handling failures gracefully? In this guide, we'll explore Kubernetes concepts through the lens of a real deployment. A microservices architecture with Redis caching, image processing workers, and a front-end API, all running on Azure Kubernetes Service. You'll understand not just what Kubernetes does, but why each piece exists and how it all fits together. What problem does Kubernetes solve? Imagine you've containerized your application using Docker. Great! But now you need to run it in production. You spin up a VM, install Docker, and start your container. What happens when the container crashes? What happens when traffic spikes and you need more instances? What happens when you need to update to a new version without downtime? You could write scripts to monitor containers and restart them. You could set up a load balancer to distribute traffic. You could implement blue-green deployments for updates. But now you're building an orchestration system from scratch. That's what Kubernetes is, a battle-tested orchestration platform that handles all of this for you. It watches your containers, restarts them when they fail, distributes traffic across healthy instances, and provides declarative APIs for deployments and updates. The key word is declarative. You don't tell Kubernetes the steps to take. You tell it the desired state. I want 3 replicas of this container running, exposed via a load balancer. Kubernetes figures out how to make it happen and continuously works to maintain that state. The Saturn core concepts, pods, deployments, and services. The fundamental unit in Kubernetes is not a container, it's a pod. A pod is one or more containers that share networking and storage. Most often, a pod contains a single container, but you might have multiple containers in a pod when they're tightly coupled, like an application container and a logging sidecar. Pods are ephemeral. They can be deleted, rescheduled, or crash at any time. You don't manage pods directly. Instead, you create a deployment. A deployment is a declarative specification for pods. You say, I want 3 replicas of this Redis container. The deployment creates a replica set, which creates the pods. If a pod dies, the replica set creates a new one. If you update the deployment with a new container image, Kubernetes performs a rolling update, gradually replacing old pods with new ones. This is exactly what we did in our AKS cluster. We created a deployment for Redis with 1 replica, a deployment for IMG proxy with 2 replicas, and a deployment for the front-end API with 2 replicas. Kubernetes scheduled these pods across our cluster nodes and kept them running. Now, pods have IP addresses, but these IPs are ephemeral. When a pod is replaced, it gets a new IP. So how do other pods or external users reach your application? That's where services come in. A service is a stable network endpoint that routes traffic to a set of pods. You define a label selector, like app equals Redis, and the service finds all pods with that label and load balances traffic to them. Even as pods come and go, the service's IP or DNS name stays constant. There are different types of services. A cluster IP service is internal to the cluster. We use this for Redis and IMG proxy because they don't need to be accessed from outside. A load balancer service provisions a cloud load balancer with a public IP. We used this for our front-end API so users could reach it from the internet. Now we are building a real system, Redis, image processing, and APIs. Let's walk through our actual deployment to see these concepts in practice. We started with Redis, an in-memory cache. Our front-end API would use Redis to cache expensive operations. We created a Redis deployment with one replica and exposed it via a cluster IP service. The service DNS name was Redis service, so any pod in the cluster could reach Redis at Redis service :6379. Next, we deployed IMG Proxy, an image resizing service. We created a deployment with two replicas. Each replica was a pod running the IMG Proxy container. We specified CPU resource requests of 100 millicores, meaning each pod needs at least 1/10 of a CPU core. This is important for scheduling. Kubernetes won't place a pod on a node that doesn't have enough free resources. We also defined resource limits of 500 millicores, meaning each pod can burst up to half a CPU core but no more. This prevents a single pod from starving others. And we exposed IMG Proxy via a cluster IP service so the front end could reach it. Then came the front-end API, an ASP.NET core application. It had endpoints for image processing that called IMG Proxy and used Redis for caching. We built a Docker image for ARM64 architecture because our AKS nodes were ARM64-based D2 plus V6 VMs. This is a key detail. Container images must match the CPU architecture of your nodes. An x86 image won't run on ARM64 nodes without emulation, which is slow and often unsupported. We created a deployment with two replicas and exposed it via a load balancer service. Azure provisioned a public IP, and suddenly our API was accessible from anywhere. We hit the endpoint, requested an image resize, and the request flowed through the front end to IMG Proxy, with results cached in Redis. 3 microservices working together, all orchestrated by Kubernetes. Davanti health probes and self-healing. One of Kubernetes' most powerful features is self-healing, and it's enabled by health probes. We configured liveness probes and readiness probes for our pods. A liveness probe checks if a container is still alive. For Redis, we used a TCP socket check on port 6379. Kubernetes periodically tries to connect. If the connection fails multiple times, Kubernetes assumes the container is dead and restarts it. A readiness probe checks if a container is ready to serve traffic. Our front-end API had an HTTP readiness probe on the /health endpoint. During startup, the probe fails because the app is still initializing. Kubernetes doesn't route traffic to the pod yet. Once the app is ready and the probe succeeds, Kubernetes adds the pod to the service's load balancing pool. This distinction is crucial. Liveness controls whether to restart a container. Readiness controls whether to send traffic to it. A pod can be alive but not ready, like during startup or when it's overloaded. We saw self-healing in action when we manually deleted a pod using kubectl delete. Within seconds, the deployment noticed a pod was missing and created a new one. The replica count specification said, "I want 2 replicas," and Kubernetes enforced it. SaaS, scaling, horizontal pod autoscaling, and cluster autoscaling. Scaling in Kubernetes happens at 2 levels, pods and nodes. Horizontal pod autoscaling, or HPA, scales the number of pod replicas based on metrics like CPU usage. We created an HPA for IMG Proxy targeting 50% average CPU utilization with a range of 2 to 10 replicas. Here's how it works. The HPA queries metrics from the metric server, which collects resource usage from each pod. If average CPU usage across all IMG Proxy pods exceeds 50%, the HPA increases the replica count. If usage drops below 50%, it scales down. This happens automatically, continuously, without manual intervention. But what if you scale up to 10 replicas, and your cluster nodes don't have enough CPU or memory to run them all? That's where cluster autoscaling comes in. We enabled the cluster autoscaler in AKS with a minimum of 1 node and a maximum of 3. When we first deployed, all our pods fit on 1 node. Then we deployed IMG proxy with resource requests that exceeded the node's available capacity. The pods entered a pending state because Kubernetes couldn't schedule them. The cluster autoscaler detected this, realized more capacity was needed, and automatically added a second node to the cluster. Within a few minutes, the new node was ready and the pending pods were scheduled. This two-level scaling is elegant. HPA scales workloads based on demand. Cluster autoscaler scales infrastructure based on workload requirements. Together, they adapt your cluster to varying load. Now, networking, CNI, DNS, and service discovery. Kubernetes networking can seem like magic, but it's built on standard technologies. Each pod gets its own IP address from a pod network. In AKS, we used Azure CNI, which assigns Azure VNet IP addresses directly to pods. This means pods are directly addressable from other resources in your VNet, which simplifies networking but consumes more IP addresses. Within the cluster, DNS is handled by Core DNS. When you create a service named Redis service, Core DNS creates a DNS record. Any pod can resolve Redis service to the service's cluster IP. This is how our front end found Redis and IMG proxy by DNS name. For external access, load balancer services integrate with the cloud provider's load balancer. In Azure, when we created a load balancer service, AKS provisioned an Azure load balancer, assigned a public IP, and configured it to forward traffic to our front-end pods. The load balancer health checks the pods using our readiness probe and only sends traffic to healthy ones. Demo AKS specifics, managed control plane, and node pools. Azure Kubernetes Service is a managed Kubernetes offering, which means Microsoft runs the control plane for you. The control plane is the brain of Kubernetes, the API server, scheduler, controller manager, and etcd database. In a self-hosted Kubernetes cluster, you'd run and maintain these components yourself. With AKS, they're fully managed, highly available, and you don't pay for them. You only pay for worker nodes, which are organized into node pools. A node pool is a group of VMs with the same configuration. We created a single system node pool with D2PLS_V6 VMs. We could have created additional user node pools with different VM sizes, like GPU nodes for machine learning workloads or memory-optimized nodes for databases. AKS also handles upgrades. You can upgrade the Kubernetes version of your cluster with a single command, and AKS safely drains nodes, upgrades them, and brings them back online. It integrates with Azure services like Container Registry for storing images, Azure Monitor for logging and metrics, and Entra ID for authentication. Ayers, lessons from real deployment. Our deployment taught several practical lessons. First, architecture matters. We chose ARM64 VMS for cost savings, but this required rebuilding our Docker images for ARM64. Always match your image architecture to your node architecture or use multi-arch images. Second, resource requests and limits are critical. Without requests, Kubernetes doesn't know how much capacity a pod needs and might overschedule nodes. Without limits, a misbehaving pod can consume all resources and starve others. Define both. Third, health probes are non-negotiable for production. Without them, Kubernetes can't distinguish between a healthy pod and a broken one. Traffic gets routed to failing pods, and users see errors. With probes, Kubernetes only sends traffic to healthy pods and automatically recovers from failures. Fourth, declarative configuration is powerful. We defined everything in YAML files, deployments, services, HPAs. We could version control these files, review changes, and apply them with kubectl apply. This makes infrastructure reproducible and auditable. Fifth, start small and scale as needed. We ran our entire workload on one node initially. When we needed more capacity, the autoscaler added it. Don't over-provision up front. Let Kubernetes scale dynamically. Conclusion: Kubernetes is complex, but its core ideas are straightforward. Pods run your containers. Deployments manage pods declaratively. Services provide stable networking. Health probes enable self-healing. HPAS scale workloads. Cluster autoscalers scale infrastructure. AKS takes this further by managing the control plane, integrating with Azure services, and simplifying operations. You focus on your application, and Azure handles the underlying Kubernetes infrastructure. When you deploy to Kubernetes, you're not just running containers, you're declaring desired state and letting an orchestrator continuously work to achieve it. Containers crash, Kubernetes restarts them, traffic spikes, autoscalers add capacity, updates needed. Rolling deployments ensure zero downtime. This is the promise of Kubernetes: resilient, scalable, self-healing applications with declarative configuration. And when you understand the building blocks, from pods to services to probes to autoscaling, you can architect systems that truly leverage this platform. In your next interview, when someone asks, "How does Kubernetes achieve high availability?" you'll know. Replica sets maintain pod counts, health probes detect failures, services load balance across healthy pods, and the declarative model ensures the system continuously self-corrects toward the desired state. That's Kubernetes in action.